Hola amigos! Welcome to our video on acceleration. This is going to be an exciting video, and we're going to move fast, so you better watch out. Get it? Move fast. Acceleration. Actually, common myth. Acceleration does not refer solely to speeding up. Acceleration is also the term to describe slowing down. Mind blown right there. Velocity. We've been talking a lot about velocity. What is velocity? Velocity is speed with a direction, right? It's how fast you're going and in which direction you're going in, right? Well, velocity is not always constant. In fact, it almost never is constant. Velocity is usually always changing, meaning you're usually not going the same speed all of the time, okay? Usually you're slowing down, speeding up, slowing down, speeding up, in whatever vehicle you're moving in. Whether it's you don't always walk at the same speed, you don't always run at the same speed, and you definitely don't drive always at the same speed. So, but your velocity is really never really constant. Usually acceleration is playing a part into your movement. Acceleration describes how fast velocity changes. Another way to write that out would be the rate of change. So the rate is the same thing as when I'm saying how fast velocity changes, it's the same thing as the rate at which velocity changes. This is our formula for velocity. I'll walk you through what each variable stands for. Remember, the line at the top stands for average, and the A, as you can probably guess, stands for acceleration. So average acceleration is your delta V, this is velocity. Remember, delta means change. So it's your change in your velocity divided by, and this is delta, so it's change, and the t is still time. So divided by your change in your time. Another way we can write out this equation is to break apart the delta into its component parts. Remember, delta means change. So when we're ever doing a change of something, it's always the final minus the initial. And remember, final and initial are relative terms. So when I'm talking about the final time and the initial time, or the final velocity and the initial velocity, I'm really referring to the beginning velocity at this particular moment where I'm examining the acceleration, and then the final velocity at that same particular moment that I'm examining the acceleration. Because you could be given a graph where you're looking at the acceleration only at this particular point, in which case this is your initial and this is your final. Okay, if you're looking at the graph and I want to say what's my average acceleration over my whole trip, then this is your initial and this is your final. So final and initial are relative to the part of the graph that you're actually looking at. So let's do a very simple average acceleration problem. If you start with a velocity of 0 meters per second, by the way, what does that mean? If you're going 0 meters in 1 second, it means you're not going anywhere. Okay, so we start from a stop. We start at 0, right? And we end up going 10 meters per second. And it took you 5 seconds to reach that velocity. What's your average acceleration? Well, here's our formula, right? Delta V over delta T, which just stands for final velocity minus initial velocity and final time minus initial time. You need to label what you're given. That's super critical. We start with a velocity of 0 meters per second. We have our initial velocity. So write that off on the side. We end up going 10 meters per second. That's our final velocity. The baby's not happy about this. And it took you 5 seconds to reach that velocity. It took us 5 seconds. Okay, so that's not TF or TI. That's our change in time. It took us a total of 5 seconds to reach that velocity. So we have VF, we have VI, and we don't have these two individually, but we have delta T, which we can use. So we can use these to calculate average acceleration. It's final velocity minus initial velocity divided by our change in our time. This gives us 10 meters per second as our change in velocity. 5 seconds is our change in time. Now, it's so important in physics. It's crucial to understand your units, okay? So what's really happening here? When we do 10 divided by 5, we get 2. And then we end up with meters per second per second, which really comes out to meters per second squared. Okay, meters per second squared is the same thing as meters per second second. Okay, so meters per second squared, what does that actually mean? What does this unit mean? Well, I think it's important that not only do you understand how to calculate acceleration, but you know exactly what that unit's standing for. Let me draw you a picture of what's happening. Here is the person who is starting with 0 meters per second, okay? He's not moving at all, 0 meters per second. He ends up going 10 meters per second, okay, and it takes him 5 seconds to get here. So here he's 0 meters per second. Here, the guy is going 10 meters per second, right? Okay, so what this means is every second he speeds up 2 meters per second. That's why that's why it's second squared, okay? For every second, he speeds up 2 more meters per second. So he starts at 0 meters per second, and then after 1 second, he's supposed to speed up 2 meters per second. So what's 2 meters per second plus 0 meters per second? Well, that's 2 meters per second. Now in the next second, he speeds up another 2 meters per second. So now he's going 4 meters per second. Then after the next second, he goes 6 meters per second, 8 meters per second, and ends up going 10 meters per second. So that's what this means. 2 meters per second squared means for every single second, he speeds up 2 more meters per second. Okay, so that is what acceleration looks like. We're going to do a more complicated problem now where we actually have to rearrange the acceleration equation to solve for a different variable. Now we've done this with our velocity formula, so it's going to be very, very similar. So first thing we're going to do is we want to make sure that we label everything in our problem first. So I'm going to read through the problem and underline any kind of number that I've been given and then label what that number stands for. So Gary was delivering snow cones in his truck, but a chicken crossed the road and he had to stop suddenly. He was originally driving 35 miles an hour, so I'm going to box that. And it took him 35 seconds to stop. What was his acceleration? Okay, I know I'm going to be looking for acceleration. Okay, what else am I given? 35 miles per hour. That says he was originally driving. That means that's my initial velocity. Okay, and it says it took him 35 seconds to stop. That's my change in time. If it tells you it took him this long to do this, that's always your change in time. Initial time and final time would be like if they gave you actual, like a certain time of day. Like he finished at 3:05, well, that would be your final time. He started at 2:35, that would be your initial time. And then you could subtract to find your change in time. But here they already give us change in time. But if you notice, if we look at our formula here, average acceleration is our final minus our initial divided by our change in time. We have this change in time. We have our we have our initial, and we're looking for average acceleration. What variable are we missing? If we're looking for average acceleration, then we need to have our final velocity. This problem actually gives you the final velocity, but it doesn't give you a number. If you read it carefully, you can see what the final velocity was. Gary was delivering snow cones in his truck, but a chicken crossed the road and he had to stop. And it says it again later. He was originally driving 35 miles per hour and it took him 35 seconds to stop. So what's his final speed? It's 0. Okay. If they say it took him 35 seconds to stop, that means we're stopping our speed. So our final speed 0. In some other problems, the initial velocity will be 0, and the way they'll say it is they'll say the object started at rest. What it means to start at rest, it means to start from 0. Okay, so be careful to look for those. So now that we have these, let's plug it into our formula. We're looking for average acceleration. Here, let's say we're given our final is 0. Our initial was 35. Oh, I put meters per second. Sorry. It's got to be the same unit, miles per hour and miles per hour. So Okay, 35 seconds on the bottom. Now, I have an issue here. The issue is my units aren't the same. This is miles per hour, and seconds. Here, our unit of time is hours. Here, our unit of time is seconds. So I'm just going to go ahead and convert. You have to convert any of these to meet the other units. So you could do miles per second on the top, but that's a little more complicated. So I'm just going to change the seconds to hours. So here's 35 seconds. I need to change it to hours. So seconds needs to go on the bottom. I know there's 60 seconds in 1 minute. That doesn't get me to hours, so I need to go another step. I know there's 60 minutes in an hour. I'm going to put minutes on the bottom so they cancel out. And now I'm in hours. So I multiply the top, and it's 35 hours. I multiply the bottom, and that's 3,600. Okay, and so I do 35 divided by 3,600. And I get a very small number, 0.00, and then I have a bunch of decimals. How many decimals am I going to use? I started off with 2 sig figs, so I have to end with 2 sig figs. So I'm only going to have 2 significant figures in the number. This is hours. So this is going to replace this value for time, because you really can only do your problem if your units are matching. So 0.0097 hours. This comes out to negative 35 miles per hour, divided by 0.0097 hours. Okay, and let's plug that into the calculator. And I get negative 3,608 miles per hour squared. But remember, this has 4 sig figs, and both of these have 2. And our rule is when you're multiplying or dividing, you need to have the same number as the fewest number of sig figs. So this has 2, this has 2, our answer has to have 2. So I'm going to rewrite it as 3,600 miles per hour squared. This is our right answer because it only has 2 sig figs. Okay. All right. Now we're going to look a little bit conceptually about what's happening in velocity and acceleration. Actually, let me go back. This is very important. This was negative 3,600 miles per hour squared. What does that mean, negative? Well, a negative acceleration means that it's accelerating in the left area. We're accelerating in the opposite direction. So here's Gary. Gary's driving 35 miles per hour in a positive direction, meaning he's going this way. Okay? If his acceleration was also positive, that means he would be going faster. If, in this case, his acceleration is negative, that means he's accelerating against his direction. Do you see that? He's accelerating in the opposite direction, so that means he's slowing down. So if your velocity is positive and your acceleration is negative, the acceleration is working against the velocity, and so you're slowing down. If the velocity is positive and your acceleration is positive, then he will be speeding up because the acceleration is working with the velocity. This is a graph that kind of shows you what I'm talking about. Here our velocity is in the positive direction. Positive means, for our purposes, the positive means the right side of the origin, and negative means the left side of the origin. Okay, the origin is where we're starting, right? So positive, so if here's our origin, positive is this way, negative is this way. Okay? So if we're going to the right direction and we're accelerating to the right, then that means we are speeding up. Okay? In this other picture, we're going to the right direction, but we're accelerating in the opposite direction. Do you see that? We're accelerating in the opposite direction. That means your car is slowing down. Here, we're going to the left direction, and we're accelerating in the left direction, so we're speeding up. You should see a pattern here. If acceleration and velocity have the same sign, they're speeding up, okay, on both of these. When acceleration and velocity have opposite signs, they're slowing down. That's because the acceleration is working against the direction of the speed. So here velocity is going to the left, acceleration is to the opposite direction, the right, so we're slowing down. That is very, very important. So you'll need to memorize when velocity and acceleration are the same direction, they're speeding up. When they're opposite directions, they're slowing down. And that's what this here is for. This little graphic is to help remind you vectors matter. Negative velocity means that we're moving to the left. Negative acceleration just means that we are accelerating to the left. Okay, and the same thing could be said if it's positive, then it's to the right, and if it's positive over here, it means we're moving to the right. Okay, so what is happening when velocity is negative and acceleration is negative? When both of them are negative, that means we're speeding up. And how do I know that? Because they're the same sign. Okay, it means we are accelerating in one direction and we're moving in one direction, so we're speeding up. Here's my object. And in fact, we're speeding up to the left. So I'm moving this way and I'm speeding up this way. Okay. Think of acceleration as like a push force. So if I'm moving to the left and I get pushed to the left, I go faster, right? Now here's velocity is negative and acceleration is positive. That means we know we're slowing down, right? We know we're slowing down because they're opposite signs. Which direction are we slowing down? We're slowing down to the left. How do I know that? Well, velocities, when it's negative, it means we're moving to the left. Okay, I'm moving to the left. But acceleration is the push. Okay, so let me show the push this way. Let's say in the first example, I'm getting pushed to the left and I'm moving to the left, I speed up. Here, I'm moving to the left, but I get pushed backward, which means I'm slowing down. See how acceleration's going to the right and velocity's going to the left. Okay, same thing over here. When they're both the same sign, we're speeding up. When they're opposite signs down here, they're slowing down. We're speeding up to the right because we're moving to the right. And then we get a push to the right, so we're speeding up. And the other one, we're still moving to the right because velocity says positive, but we're getting our push, our acceleration is backwards, so we're slowing down. Okay, so we're slowing down to the right and we're speeding up to the right. All right, now let's look at some graphs. We've been looking at position time graphs like this. It's important to note that a position time graph is graphing the slope of a position time graph is graphing velocity, right? When the slope, this is important, when the slope is flat or constant, that means our velocity is constant. Means our velocity is constant. Okay, if velocity is constant, not changing, if we're not changing our velocity, that means our acceleration is 0. Remember, acceleration is how much our velocity is changing. So if you see a straight line, that means that your velocity is not changing. Okay, the slope is steady. It's constant. So here, our velocity is, we're moving to the right, but our velocity is constant. It's never changing. That means our acceleration is 0. Okay, our black line here, velocity is 0. We know it's 0 because it's a horizontal line, which means our position's not changing. So we're not moving at all, but guess what? It's still constant, right? Our speed of not moving is constant, so our acceleration is 0. Here our velocity is negative. We're moving away from our position, but we're moving at a constant speed because it's a straight line. So I should have used straight, not flat. When slope is straight, our velocity is constant and our acceleration is 0. Anytime you see a straight line, acceleration is 0 because you're not changing your speed. Okay? These graphs have acceleration. They're changing velocity because guess what's changing? Slope. When you have a curved line, your slope is changing. So if the slope of a position time graph changes, our velocity is changing. So let's look at this first graph over here on the left, okay? This first graph, we see that in the red line, we see that our slope is getting steep. We have a steep slope in the positive direction. This means if our slope is getting steeper and steeper, that means our velocity is increasing. So our velocity is increasing. Its speed. And we're increasing it in the positive direction because it's going upward, right? And our acceleration is positive because we're increasing our speed, right? So they're going the same direction. So we're increasing our speed. Let's look at this next one. Here, we still have a steep slope. Our slope is getting steeper and steeper, but it's getting steeper in the negative direction. So here, we are increasing our speed, but our velocity is negative because we're going away from our origin, right? Here's our origin. This is 0. This is 1 meter, 2 meter, 3 meter, 4 meter. This is -1 meter, -2 meters, -3 meters. We're moving in the opposite direction. So we're going negative. What sign does our acceleration have to be if we're increasing our speed in the negative direction? Our acceleration has to be negative so that they're the same direction, so they're increasing their speed. This other graph, as you can probably guess, shows objects slowing down. Our slope is decreasing here. It's decreasing in both of the graphs. It's decreasing because it's almost becoming a flat line. See that? So slope is decreasing in both of these. In the top one, slope is decreasing in the negative direction, right? We're going away. We're going further and further away. And here, slope is decreasing in the positive direction. Okay, we're getting closer and closer to our point of origin here. So in the top one, we're decreasing our speed in the negative direction. So velocity is negative. Acceleration is positive. How do I know acceleration is positive? Well, if I'm slowing down, that means my signs have to be opposite. So acceleration has to be positive. Here we're decreasing in the positive direction. So if we're slowing down, my acceleration is going to have to be negative. And that's it for our video on acceleration. Have a great day.